Maybe people. Okay. Yep. Okay. Yeah. Okay. Hello, everybody. My name is Ed Law from Princeton University. So on behalf of the summer school and also together with Dr. Dagaut and on behalf of the Combustion Institute. So we welcome you to this webinar, the combustion series. It's really very exciting that after all the lockdown, year and a half, and now things seem to be looking up. And what better way to sort of welcome the future or welcome back the previous life with the combustion course like this. So we're very fortunate again to have Dr. Dagaut to give our chemistry part of it, especially he is the president of the Combustion Institute. You know, symbolically, it is it's just so exciting, and personally that he is so busy. You know, initially when I invited him, he's a little bit worried, but then for the community, he played the leadership role and say, okay, I'll do it. So here he is. You can see that. Dr. Dagaut really doesn't need much introduction. I mean, he is a leader in combustion chemistry, working in also all aspects of combustion, oxygenates, hydrocarbon fuels, and the pollutants and all that. And of course, the leadership roles, being the directors of many research organizations in France, and also in terms of publications, a lot of publications. I saw that 290. That's a large number of publications with that. So then what really I look over, and you guys can look it over too, bio that he has gotten that two aspects I want to point out, which really was very impressive. One is he got the Edgerton Medal, right? In Edgerton Medal. That's quite a recognition. Now, those of us in combustion, we know to get one of those gold medals, it's usually when I was young, the senior guy said, that is really the recognition. Usually you get it at the end of your career. When you're really old, you get it for the gold medal. But he got it very, very early. And I was also fortunate to get it. And then I look at it, he got it even earlier than I did, after the PhD time. So that's my really a salute to him. And then also the other big accomplishment is being the president of the Combustion Institute. Again, it is a recognition that those of you, I mean, you guys are all in the Combustion Institute. One thing we value in terms of leaderships, we choose the leaders to be good researchers first. Okay, that's important. Rather than certainly it has to have good administrative ability, but leader researchers first. So that is again a big recognition of Dr. Dagaut's accomplishments and how it's being recognized. So again, I wouldn't take up too much of the time. I think I'll just leave the, whatever you call it, podium, leave the screen to him, Dr. Dagaut. Thank you so much for making yourself available. So from now on, he runs the show. And he, at a certain point, maybe take a break and all that. It's all yours, Philippe. So
all right.
Thanks again, Philippe.
Thank you very much for this kind introduction, and then we will start. So first of all, I must apologize because I'm not really used to give lectures with this system. So sometime maybe I will make mistakes, will be speaking too fast or moving too fast from one slide to another. I will try to avoid that, but well, it's a live show, so things can happen. So this is what we will be going through. So today I will introduce the different aspects of combustion. What is combustion? Why do we use combustion? Some statistics. I will introduce chemical kinetics and modeling, global fuel properties that we consider, and the composition of fuels, which have much importance on their reactivity and also on pollutants formation. There are specific pollutants that can be produced, and this is very much related to the fuel composition. A second session will concern experimental techniques for kinetics models assessment. And then I will present the different popular techniques which are used nowadays, like shock tube and rapid combustion machines, which are used for different things, measuring ignition delays, but also species. Flow reactors, tubular flow reactors, and stirred reactors, which also allow the probing of the chemistry. And to some extent, with plug flow reactor, we can reach ignition delays. Flames, simple flames, simple laboratory flames will be described, and I will give an overview of their advantages and disadvantages. The third session will be on modeling. So after general information, I will present temperature dependencies of elementary reactions, pressure dependencies, different kinetic analysis which can be performed, such as sensitivity analysis, rate of consumption or production. Pressure and temperature dependencies in relation with reaction pathways. So when you are operating under relatively low temperature, the reaction pathways differ from what they are in high temperature. And also there are some dependencies which can change dramatically. I will spend some time on the low temperature oxidation mechanism, which are still very complex to describe in details. We will have a look at pyrolysis and high temperature oxidation processes, which are much easier to describe. And then we'll spend some time comparing the chemistry of single fuel and multi-fuel components oxidation. And you will see that some of the components, especially the more reactive ones, can influence very much the overall oxidation rate. The fourth session will concern pollutants formation and also ways to reduce them. And among them, we will consider NOx, unburned hydrocarbon and soot, and finally the effect of some traces, species, such as NOx or ozone. Those can affect ignition significantly, and we will describe the mechanisms which are responsible for that. And finally, we will have a look at commercial fuels combustion, the use of surrogates, and a range of biofuels for which there has been more and more papers describing their chemistry of oxidation in the literature. So first of all, combustion. Well, it goes back to prehistorical days, and the quest for fire was the title of a French movie by Jean-Jacques Hano, published in 1981. And at that time, being able to keep fire burning was very important to survive. But nowadays, where is combustion? Well, you can see on this Christmas picture that, well, of course, it's here in the fireplace, candles, different candles on this table. But it's, well, this is this is trivial. But combustion was used also to produce glass, to produce these forks and knives, spoon, metallic material, and also glass or ceramic plates on this table. So combustion is almost everywhere here, and outside it would be about the same. The oxidation of a given fuel ultimately leads to the formation of carbon dioxide and water, but also heat in the case of organic fuels like hydrocarbons. Another definition can be an exothermic redox reaction between a fuel, which is the reductant, and an oxidant, which can be oxygen, for example, oxygen from air. Incomplete combustion yields a large range of species, unburned hydrocarbons, but also particulates, soot particulates. And NOx also can result from the oxidation by oxidation of molecular nitrogen. And these chemicals are sent to the troposphere, and there they can undergo additional reactions. And you will see in the next slides that some of these interactions that are summarized here appear both in combustion and also in troposphere. There are many interactions, like the formation of RO2 here by peroxidation of radicals from the fuel. These can react with NO and produce NO2, which in the atmosphere is photolyzed, give back NO and oxygen atoms, and these oxygen atoms are responsible for the formation of ozone, the major oxidant in the troposphere. But it's extremely complex what can be observed, and we'll try to give you a flavor of what's going on there. Combustion involves chemical reactions, thermochemistry, and reaction kinetics, heat and mass transfer, radiation. So it's lots of different physics and chemistry aspects. The overall or global chemical equation, like for hydrogen, 2 molecules of hydrogen reacting with 1 molecule of oxygen, gives 2 molecules of water, or that describing the oxidation of methane, forming carbon dioxide and water, is only a mass balance. But it doesn't describe what's going on in reality. And we will see that it's much more complex. And these global reactions cannot explain the products, cannot explain the intermediate, cannot explain some of the pollutants which are formed during the combustion processes. We use a range of parameters to describe the conditions when we perform oxidation or combustion. The first one is occurrence ratio. Occurrence ratio is described here as a ratio of fuel concentration over oxygen concentration, and this ratio divided by the same ratio at stoichiometry. When you have just the amount of oxygen needed to burn all the fuel, like here where you need 1 mole of O2 to burn 2 mole of hydrogen. And for conditions like furnaces, people are using excess air, which is simply the opposite of the equivalence ratio. So depending on the ratio of oxygen to the fuel, you will be in stoichiometric condition, where phi equal 1 or lambda equal 1. So you just have the amount of oxygen to burn all the fuel. If you have more fuel than oxygen provided, then there will be a leftover. And well, here I simply considered it was hydrogen which was left over. And then phi is higher than 1. And we say that we operate in fuel-rich condition because we have more fuel than under stoichiometric condition. And now if we have more oxygen than needed, we have excess of oxygen, and we say that we are operating fuel lean or in excess of oxygen. And some oxygen that you introduced initially is still available. The combustion of methane, for example, involves a long sequence of elementary reactions. There are initiation reactions, propagation reactions, branching reactions, and termination reactions. And I will show you what they look like. They involve stable species and unstable species like atoms and radicals. These reactions proceed with reaction rates ranging from slow. For example, the reaction of an hydrocarbon with O2 is a slow process, fortunately. Otherwise, every hydrocarbon would burn outside, which it doesn't. And this means that this reaction is very slow. Or very fast reactions like radical reactions or atom reactions. Why combustion? Transport accounts for about 20% of the total global primary energy consumed. About 23% of CO2 emissions and 7 billion tons of CO2. More than 99.9% transport is powered by internal combustion engine for land and marine transport and air transport by gas turbines. This is a very interesting paper by Professor Calcati at Oxford University. He reports here in this table the maximum takeoff weight of different planes, the volume of fuel which is transported, the weight of fuel, and the energy content of the fuel, and finally the weight of battery with the same energy content as computed here. And finally, the ratio between the weight of the battery to the maximum takeoff weight. So you can see that if you go from a relatively small airplane, the maximum takeoff weight is about 20 tons, whereas it is 76 for middle range aircraft, and it's almost 600 tons for the huge Airbus 380. And then when you consider the weight of battery that could power such an aircraft, you can see that it's getting really huge. Here, it's almost 300 tons. 1,500 tons and 1,800 tons. And the ratio is increasing for this one, 14 to 19 and then 31. So clearly nowadays we are unable to get airplanes flying, airplanes of the size we are used to fly using batteries. Batteries can be used for some let's say plane activities, but certainly not for flying. APU can work on batteries, for example. So the global demand for transport energy is about 105 terawatt-hour of liquid fuel energy per day, which means 38,000 terawatt-hour per year. And in 2016, the consumption of wind and solar energy together reached 1,300 terawatt per year. And the consumption of electricity reached almost 25,000. So you can see that there is quite a gap here, and it will be difficult to accommodate, I believe. This is a breakdown of the consumption of energy in terawatt per hour in the world. And you can see that depending on the region where you live, it can be quite different. And darker is the blue color, more energy is consumed. You see, it's the case for the US and also for China. The world energy production is shown on this plot, and you can see that it's growing steadily. And you can see also that the fraction of electricity production in this area here is increasing much faster than in the other region. And this region is Asia. What is the fraction of electricity of renewable in electricity production? Well, you can see it's about 25% nowadays, and it should be increasing in the future. What do we burn? Well, we burn lots of oil, lots of oil. Well, there has been in the around 2000, there has been debate about the available oil and the demand, and when will we reach the peak oil. So at some stage it was predicted that it was around 2000, and then maybe later. It's not really clear when it will happen, but we are close to this peak oil. And the total oil production, the total oil product demand by type of product is given on this plot. Well, these data are a bit old, but there is not huge difference nowadays. So for transportation, it's about 2/3. About 12% for heating, and for other applications, it's about 27%. Well, today still about 98% of transport fuels are oil derived, gasoline, diesel. They come from oil. Here, these are projections by the US Energy Information Administration. And you can see that they predict that the energy use will increase overall, and the production of energy by nuclear power station will increase. The use of renewable should increase faster. The use of natural gas steadily increase. And what is maybe surprising is that the predictions show that coal use will still increase pretty fast, and oil use will also increase. And this is the same information in 2010, so around here. And you can see that coal represents 25% of 26% of energy used before natural gas, and liquids derived from oil represent 35%, nuclear 6%, and renewable 10%, and it will be increasing. Okay. So to try to keep sustainability, we need to burn cleaner, and we need to burn better, more efficiently, increase energy per kilogram of whatever the fuel is. EU regulations have been evolving with time, and we plot here the evolution of the different restrictions or standards in terms of particulates, NOx, hydrocarbon. Well, in fact, it should be CO2, I believe here, and CO emissions as a function of distance. And you can see that starting from Euro 4, where this area was pretty large, now we are dealing with Euro 6, which is a much smaller fraction. But well, if you compare the surfaces, which is probably not the best way to compare things, but we have divided the surface by about a factor of 4. Combustion can produce particulates, but not only combustion produces particulates. This is an overview of the annual mean particulate measurements, and well, the red dots show the regions where it's the highest, and so you can see that in Eastern Europe, like Poland, there are lots of particulates. They still burn lots of coal. Also Greece, in Turkey, and some area in Italy, France, Spain. There are high concentration of particulates. So some of them can come from combustion, but there are other sources of particulates, like erosion, for example. So industry is producing particulates, agriculture, air and ground transportation. Beside soot, we have also particulates coming from tires, from brakes, homes where you burn, maybe you will burn wood, or well, in Eastern countries they burn coal still. Wildfires, those you've seen terrible wildfires in the US and in Australia, but also in eastern part of Europe, like Siberia, for example. Soil erosion, as I mentioned, and hurricane and tornado can also be responsible for these particulates, and sea salt are also important. So you see there is a large variety of particulates, not only soot coming from combustion. And if we look on what's going on in different continents, you can see that the particulate matter of 10, 10 microns are present still in this area that I showed before, but also in India and China, in some regions of Africa, South America, Central America, and in more developed countries, there are still a fair amount of particulates which have been observed. So these particulates can have a negative effect on health. So they are classified as gas molecule, particulate contaminant, some dust, and biological contaminant. So you see soot is easier. So with a size of 0.01 micron to 0.5 micron, about tobacco smoke, that's about the same. Smoke from fires, oil smoke, fly ash coming from the combustion of solid fuels, and cement dust, which has also similar size. Regarding dust, so there are suspended atmospheric dust. They can come from different sources. As I said, soil erosion is one of them. And well, then I don't know exactly what they meant by settling dust, adding dust, but these are other type of dust which are present around. Viruses, so they are very small, and this is the reason why when somebody got one of these viruses and cough, then it can go, they can be propagated. Bacteria is a bit bigger. And all these which are causing problems of allergy are bigger size, between 10 and 100 microns. Well, the problem with these particulates is that we as human beings are naturally protected against the largest particulates, which will not go any further than, let's say, your throat, but smaller particulates will continue their way to the lungs. PM 2.5 will enter the lungs, and PM1 will even diffuse in the blood. So if these particulates were chemically neutral, if they were not carrying some active species, that would be fine. But it's not the case. On the surface of soot, for example, you will have pH, oxygenated pH, nitro pH, and all kind of very complex chemicals. And some of these chemicals are very nasty especially nitro PAH, carcinogenous species. So this is the reason why this is a big concern, the formation of particulates from combustion. Well, this is an example of measurements which were made behind an internal combustion engine. And they used different fuels. They use a conventional diesel fuel, and they got this type of behavior here. Then they increase gradually the ratio of N-gas recirculation. And you can see that the shape of the distribution of these particulates is changing, and also it is affected by the introduction of esters deriving from rapeseed methyl esters. If you increase this content of esters with increasing EGR, you can see that you are changing the position, changing the maxima, or changing the distribution of the particulates. So as an introduction, we can show the original diagram by Professor Bocorn, published in '86, where he was showing the different steps to the formation of soot particulates. You start with a fuel that you oxidize. You will produce some unsaturated species which can react and produce some aromatics. And the first aromatic they produce is benzene. And then you can continue to add some radicals on these cycles and produce polyaromatic structures like choline. And then there, at that time, it was not very clear how things were moving toward the formation of these particulates. And in this rare year, they were proposing, first of all, a process of particle inception, surface growth and coagulation. And coagulation, it means that these larger particulates will form bioparticulates. Yes. Well, these particulates are not spherical. This is part of the problem when you want to do diagnostics with these. You see your picture taken with an electronic microscope, and you can see that this is the agglomeration of small spheres, and it gives you some very complex shapes. One other aspect is the relation between the overall CO2 emission and the global population on Earth. And you can see that somehow there is a correlation between these. And well, therefore, we have much effort to do to decorrelate these two factors. Interesting is the differences between the different regions in terms of CO2 emission. And if you consider the annual tons of carbon emitted per person, you can see that in Bangladesh it's close to zero, where it's very huge in the US, and very far from the global average. All right. Greenhouse gases again. So transportation is responsible for about 14%, and within this these 14%, road transportation represents almost 70%, followed by domestic air, international air, marine, and other sources of transportation. And the rest, the rest represents 86%. To reduce CO2 emissions, we can enforce some new regulations. This is what was decided in different developed countries. And for example, in the EU, you see the different regulations that got in place until recently. And well, this means that you need to reach these numbers. You need to increase the efficiency of engines, and you can do that by improving the technology or strategy, moving to other fuels, and so nowadays there are still lots of research going on in order to go even further than this. So I go back to this schematic, and when we are dealing with chemical kinetic and modeling, we have to deal with a huge number of species. So usually, again, in combustion, you have this reaction. Most of the time, the oxidation of the fuel is driven by the reaction with OH radicals, which produces a first radical. This first radical can react with molecular oxygen to form a peroxy radical. And this peroxy radical can react with HO2 to produce an hydroxy peroxy radical, which can decompose and reform OH. You can have a recombination of these RO2 to produce these oxy radical. If it's an alkane here, it will be an alkyl peroxy, an alkoxy, radical. And these radicals can undergo decomposition or also react with molecular oxygen to form HO2, etc. If you are using exhaust gas recirculation, in the exhaust there are some nitrogen oxides present, and these can react with RO2, which are present, for example, in the engine, and you will have a formation of NO2 and RO. But these processes, and the second one is also very important, the reaction of NO with HO2. In fact, these two processes here are key reactions in the troposphere also. So you can see that some of these mechanisms are common to both combustion, low temperature combustion and atmospheric chemistry. What is not important in combustion is the photolysis of NO2, which occurs in the troposphere to produce NO and an oxygen atom. And this oxygen atom, as I said before, can react with O2 to produce the extremely aggressive molecule ozone. But this is a small piece. These reactions can go much further, and you can, after the first production of RO2 radicals, you can have a internal isomerization, which I call the H shift here, which produces a new species which can react with O2, produce a more oxygenated species, which can decompose and produce very important species here, ketohydroperoxides. But if the H shift occurs on a different carbon atom, you can get this guy, which can be peroxidized again and form this new radical, which can also decompose and produce this dihydroperoxy keto compound. And it can go on for a long time. And there is another channel, which is described here, where the first peroxidation is followed also by recombination of these RO2, which can decompose, produce RO plus O2, and then this alkoxy radical can isomerize through H shift, and the reaction goes on for a while, like this. And there are other options here. Also, this intermediate can produce an alkyl peroxy, which would be C10H15 or C10H15, for example. So you can see that there are many pathways which I have a slight problem because okay, that's better. So many pathways which can occur. So what modelers do usually, they use experimental data to compare with their modeling. But in fact, what they want to do is to use data to constrain their model. And to do that, they will be using some global parameters like ignition delays, which give you only the information how fast ignition occurs. These ignition delays are driven by initiation reactions and also reactions of radicals with molecular oxygen. Most of the time, these are the most important reactions driving ignition delays. Burning velocity is also a global parameter. It doesn't give you any information on the evolution of species concentration, function of time or temperature. It is driven by H fluxes, formation and consumption of H atoms. This is a key parameter. There are exceptions, but this one usually is the key parameter. Detailed information are, for example, species concentration. These are the results of all the processes which can occur, like initiation. So initiation is a reaction where you start from the fuel and you can decompose it, produce an H atom and a radical. It can also decompose and produce two radicals, like for example, ethane, C2H6, which will decompose from two methyl radicals, CH3 plus CH3. And finally, the reaction of the fuel with O2, which is a slow reaction, giving a radical in HO2. Propagation reactions are reactions where you use an active species, which is an atom or a radical, and you produce an active species, so the same amount of active species on both sides of the equation. And it can be the reaction of the fuel with OH, which will give HO2 plus the radical from the fuel. Finally, the last class of reactions we have is the reaction of termination reactions, where you have two, a radical and an atom which form a stable species, or two radicals which recombine and form a stable species. In fact, terminations and initiations are the same reactions. You see these two reactions and these two reactions, but they operate in opposite direction. So different types of reactors, like shot tube, plug flow, perfectly stirred reactor, flames, laminar premixed or post flow, rapid compression machines, and some engines operating under very well-known conditions can be used to probe the validity of the mechanism, the kinetic mechanism that you propose. So I propose that we have maybe the break now, and we will continue with the chemistry, detailed chemistry of these different fuels, and starting with the simplest one, which is hydrogen. So I let the person in charge to maybe we can have a look before the break starts. We can have a look at the questions. Let's see why the increase in coal use. Well, I hope my answer is accurate. I think it's simply due to China's consumption. So I answered here. I don't know if I did the things properly or not. So we can have the break now, and we get back in about 5 minutes. Okay, so it looks like we are all back, and so I wanted to describe the main differences between global and detailed chemistry. So once again, if we consider the oxidation of hydrogen, one molecule of hydrogen reacts with half, well, 1 mole, it's easier, 1 mole of hydrogen reacts with half a mole of oxygen, and producing 1 mole of water. So this is only mass balance. It doesn't represent properly the reaction pathways, because there is only one equation. Global rate can be defined as it is here, a pre-exponential factor, a deviation of the temperature dependency from the classical Arrhenius equation, and then the exponent of activation energy divided by the temperature, and the gas constant, and that multiplied by fuel concentration and the square root of oxygen concentration. So this is the global rate, right? But in reality, even for hydrogen, there are more reactions. The first reaction, if you write it in the opposite direction, it would be an initiation, decomposition of hydrogen, giving 2 hydrogen atoms. And if you write it as a termination, then it's 2 hydrogen atoms reacting together to produce hydrogen. Same thing for oxygen, decomposition to produce 2 oxygen atoms, or recombination to reform molecular oxygen. Same thing for OH. Either you consider the recombinations of O and H to produce OH, or decomposition to produce O and H. The molecular initiation of the oxidation of hydrogen gives 2 OH radicals. Whereas the recombination of OH and H atoms produces water, and the decomposition of water can also produce OH and H. Hydrogen, molecular hydrogen can react with O atoms to produce 2 OH radicals. The recombination of OH radicals can produce O atom and water. Another molecular reaction initiation, which is H2 plus O2, can produce HO2 and H. H can react with O2 to produce OH and O. This is the most important reaction in the oxidation of hydrogen, but also it's one of the most important reactions in every system where you have hydrogen and oxygen. I mean, even for the oxidation of hydrocarbons, this is a key reaction. H2 can react with OH radical, producing H2O and H atom. H2 can react with O atom to produce OH and H. And the recombination of H and O2 can form HO2. So you see, this is the same reaction here. In this reaction, this is a branching reaction, because you have one active species here which produces, in this reaction, 2 reactive species. And here you have one very reactive species, which by reacting with O2 produce a less reactive species. There will be competition between these 2 channels, and we'll see that a bit later. HO2 radicals, which I said are not very reactive, can recombine and produce H2O2 and molecular oxygen. And finally, H2O2, which accumulates intermediately, can decompose if the temperature is high enough to produce OH radicals, which are very reactive species. So the value of the rate constant indicates how fast the reaction can proceed. Such sets of reaction with the corresponding rate constant constitute what we call chemical kinetic reaction mechanism. Okay. So for the forward reaction, the rate will be the derivative of the molecular concentration time, which is equal to the rate constant in the forward direction, multiplied by the concentration, the molecular concentration of the reactants A and B. And then if you consider the modified Arrhenius equation, you will have the pre-exponential factor for the forward reaction multiplied by an exponent of T of the temperature, multiplied by the exponential of E over RT times A, concentration of A times concentration of B. And for the reverse reaction, you will write the same thing with the appropriate pre-exponential factor and the dependence on the temperature. The equilibrium constant is usually computed from thermochemistry, and you have this equation. The equilibrium constant is the ratio of the forward over backward reactions. This value of K in forward or backward direction are determined experimentally, or they can be also computed. K is obtained from tabulations, and for example, the NASA polynomials, which are used by chemicals. In terms of thermochemistry, reactions are you can see your potential energy function of progress reaction. So you start with these two reactants here. They get closer one to the other. And this transition state has higher energy. And then it can start to decompose and produce the two species here, HF and F atom. So the overall reaction is H plus F2 giving HF plus F. So when H approaches F2, the FF bond extends and electron density moves from FF bond into the newly formed FH bond. This results in an increase in potential energy. This is what we see here. And the activation energy for the forward process is given here. According to the first law, the energy U of an isolated system is constant. And we can write the derivative of U is equal to derivative of Q plus dW, and Q will be the heat absorbed by the system, and W being the work done in the system. The second law indicates that mechanical energy can be transferred completely into heat, but heat cannot be transferred completely into mechanical energy, which means that S being the entropy, ds is higher than dq or T, and ds is equal to dq in reversible conditions divided by T, and ds is higher than dq irreversible divided by T. And the third law states that entropy of a perfect crystalline substance at 0 Kelvin is 0. So S is 0 at T equal 0 Kelvin. So the Gibbs energy G is equal to H entropy minus Ts, S being the entropy. At a constant temperature, delta G equal delta H minus T delta S. So equilibrium occurs at minimum G at constant temperature and pressure. And the equilibrium constant can be written as delta G equal to minus RT log of K. And heat capacity, there are two kinds of heat capacity, heat capacity at constant volume or a constant pressure. And their equations are given here. And Cp is equal to Cv plus R, the constant of ideal gases. And we can write the enthalpy of a reaction being that delta H T2 equal delta H T1 plus the integral between T1 and T2 of delta R Cp dt. The Gibbs energy, in fact, indicates if the reaction goes spontaneously or not. And if delta G is lower than 0, then the reaction is spontaneous. If delta G of the reaction is higher than 0, it's non-spontaneous. Now let's have a look at some of the important global fuel properties. And first of all, we will I will remind you what Cetan number and octane number means. First of all, this is a schematic representation of the evolution of the fuel concentration, which is oxidized in a, let's say, in a reactor as a function of temperature. So you introduce in your reactor a certain concentration of fuel and oxygen, and you increase step by step the temperature, and you measure the reaction of the fuel at these different temperatures. And you can see that when you increase the temperature up to around 650 Kelvin, the concentration of the fuel decreases. At about that temperature, there is a reduction of the consumption of the fuel, and its concentration is going up, sometimes up to the initial concentration, most of the time to a lower concentration than initially introduced. And then above around 800 Kelvin, you have again consumption of the fuel which occurs. So depending on the fuel structure, the chemical class of fuel that you consider, this temperature and that temperature won't be exactly 650 and 800. For example, for hydrocarbon, this is typical of alkanes. If you were dealing with ethers, it would be shifted to lower temperature. And the reaction would start probably 50 degrees below. So here we have what we call a cool flame. It's called a cool flame because this reaction is not producing much heat compared to what occurs here. And also the fuel conversion is not 100%. So we call it cool flame. This is due to peroxidation of the fuel, and some of the reactions I showed you schematically in the slides before. And here, between this maximum fuel conversion that we have at low temperature and this temperature at which we reach the lowest fuel conversion, we had a region which we call negative temperature coefficient, which means that when you increase the temperature, you have a negative effect on the fuel conversion. Let's say that these two regions, the one between 500 and 800 and the one starting from around 800, correspond to two different regimes of oxidation. Here we have an autooxidation mechanism, and this is what is necessary to auto-ignite a fuel, like we do in a diesel piston engine, when you compress the mixture of fuel and air at a given temperature, and then it auto-ignites. But this is typically what we don't want to occur in a spark ignition engine, because if it occurs, then you can destroy at least your piston and even your engine itself. And the process which is responsible for that damage is what we call knock, engine knock. Call it engine knock because if you record the pressure under these conditions, you can see that there are jumps in pressure, and it's causing noise. So this is the origin of this name. So now when about the different engine types, so spark ignition, or also called auto engines, and diesel or auto ignition engine. There are fuels which are appropriate and fuels which are not appropriate. So for spark ignition engine, you want the fuel not be reactive in this region. And fuels like isooctane are very good for running spark ignition engines. And the primary reference fuel which are used to define the octane number are isooctane and normal octane. Isooctane is this one. So isooctane is not prone to auto ignition, and so it was given an octane number of 100, whereas normal octane, C7H16, is prone to auto ignition and is not good for operating spark ignition engines. And they gave it an octane number of 0. So usually fuels that we are using have octane numbers higher than 85. For compressed ignition engines operating with a diesel fuel, then we define the certain number of 100 for normal hexadecane, which auto-ignites very easily, and we give a certain number of 0 for alpha-methyl naphthalene, which doesn't show much of cool flame. So you see the two differences here. You don't want to have auto-ignition, so you will have fuel composition which include isoparaffins, aromatics, olefins. Those are not prone to cool flame formation. And conversely, for a compressed ignition engine, you want fuels which auto-ignite very easily, like normal hexadecane. This is an example of laboratory studies where we vary the research octane number. So the research octane number is defined by the composition of the fuel. And here we defined it by the percentage of isooctane in the mixture. So it's 100 when isooctane is low, and it's 0 when it's 110. Normally 10. So. And here we plotted so we operated the oxidation in a jet stirred reactor at 10 atmospheres, probably 1,000 ppm of fuel, and we measured the concentration of CO and CO2 in the low temperature regime. So here at their maximum, and we could plot these in logarithm scale, and you can see that there is a decline of the concentration of CO and the decline of the concentration of CO2 when we increase the number. We even did some experiment with normal decaying, which has an even lower research octane number. It's negative. And after we reach a certain value of the octane number, there is a dramatic drop in the formation of CO and CO2. And this occurs between 70 and 80 research octane number. So in fact, this is the range of octane number which we can operate in an engine. So here the transition is observed around here. And there has been several kinetic modeling of these experiments. And it shows that this is due to competition between different reactions of the fuels and their intermediates. This is a summary of what this is a summary of trying to get the right size here of the reaction pathways that can occur from a given hydrocarbon. So the first step here is the H atom abstraction from the fuel, giving the first radical. And if we are at relatively low temperature, below 650 K, you have a peroxidation, your formation of the first RO2 by internal H atom transfer, H shift, you get this species which can add molecular oxygen. You get another peroxy, hydroperoxy species, which also can isomerize through H shift and produce this guy, which can decompose, produce OH radical and the ketohydroperoxide. This ketohydroperoxide can also decompose, produce OH and OQ, which can further decompose. But once the temperature reaches values above 650, some of these reactions will not proceed this way, and they will go backward step by step. And then you will have temperature range above 600 Kelvin, where this QOH will decompose and produce a cyclic ether and OH. This is mostly in the negative temperature coefficient region, and you can have also decomposition to produce a carbonyl species and OH radical. You started here by probably consuming an OH radical, and you see that here you only produce one. So this is a propagation process, which explains why we are seeing an oxidation rate which is continuously decreasing. And if you continue to increase the temperature, then this species will almost disappear, and you will have the reaction will still produce RO2 radical, and these can react with the fuel to produce hydroperoxy, which can decompose and also produce OH. If still the temperature continues to increase, then there will be some reaction of RO2 with RO2 to produce these alkoxy radicals here. But when the temperature is above 800 Kelvin, the formation of RO2 in most of the cases disappears. And then the radical, the alkyl radical, for example, here, which is formed, R, will react with O2 to produce an olefin and HO2, or will decompose to produce H and an olefin, or a radical plus an olefin. And again, this is a simplification of what we can what can be observed, in fact, where there are multiple O2 addition followed by H shift and decomposition of some of the intermediates to produce a range of species. I will present you this in more details later on. And again, this scheme, which was partially presented in the previous slide, can go further if the H atom transfer, the H shift, doesn't involve the carbon which is linked to the OH group. And then there will be open channels, and further O2 additions can occur. So clearly this chemistry is very complicated. Structure and reactivity. So again, octane number of 0 for N-heptane. It's what we call a straight chain, although in 3D it's not exactly that. The isooctane, which has an octane number of 100. This is due to the fact that most of the groups are methyl groups, and there are only 2 carbons, one secondary and one tertiary, for which the H atom abstraction can occur pretty easily. On the other one, the bond strength here is higher, and then it's more difficult to abstract this methyl radical. And once you have abstracted one of these, either these 2 or this one, and added the oxygen to this carbon, then the H atom transfer will not be very easy from this structure, which explains why it has a tendency to not auto-ignite. And in the case of the fuels used for diesel engine and to define a certain number. So we have the normal hexadecane, so you see it's a much longer chain, and more possibilities to have internal H atom transfer and O2 addition. And therefore, it's much easier to produce a strong cool flame. Whereas here we have an aromatic structure where the abstraction from these bonds here is difficult, and the methyl group also difficult to oxidize. So all in all, this is the reason why it's difficult to have these guys. So yeah, here. So this is this one is isoctane, and N-heptane is C7H16. On here I have a list of different hydrocarbons, and they are certain numbers. So you see that normal heptane it has already a high certain number. Dodecane, of course, is much better. But when you consider branched alkanes, like this pentamethyl heptane, then the certain number drops dramatically, because this structure, which is similar to that of isoctane, is not prone to cool flame. It's difficult to have H atom abstraction on these on these different methyl groups in the molecule. So N-hexadecane, I said it's one of the primary reference fuel, and we have hydrocarbons which present even higher certain numbers, like this nonadecane and ecozadecane, etc. So I said before that there are some aromatics which have less reactivity under the cool flame regime. Well, it's balanced by the fact that here we have a long side chain, and this long side chain is reacting like an alkane, whereas the aromatic group is almost unreactive. So by increasing this chain, you have an increase in reactivity in the cool flame regime. So here we have C15 plus benzene, and C14, sorry. And then the reactivity is increasing. Another example here is of an aromatic hydrocarbon is this one. But here we have a trimethyl group. So then the reactivity will decrease compared to this one, because these methyl groups are not very reactive. Now concerning the octane numbers, if we consider the research octane numbers, methane has a very high octane number. This is the reason why it can be used in spark ignition engines. As we said before, this has a low octane number. Yeah, low octane number, and 2,2,4 trimethyl pentane is isoctane, so it's the other reference fuel here. Regarding olefins, as I said before, olefins are interesting as a fuel component for a spark ignition engine, because they have they have higher research octane number. And if you compare normal heptane, which we looked at before, which has a run of 0, then if you have only one double bond, then you go from 0 to 55 or 73. So you see the big jump just by adding one double bond to this structure. So fuels, fuel composition is also varying. So you see on this graph the average carbon number of different fuels. So let's start with liquefied petroleum gas. We are around here. So it's about C4, C6. Gasoline is a bit above. Then we have jet fuel and diesel, which can extend a bit further, and all these other fuels here. So natural gas is around here. Natural gas, it's mostly methane, but not only methane, because depending on the place where you get natural gas from, its composition can vary significantly. And what we can see is that it's mostly methane plus higher alkanes, which can be linear or branched. And there can be also presence of nitrogen or even helium in some natural gas samples. Liquefied petroleum gas, well, it's region dependent. So in the US, it's mostly C3 hydrocarbons, and in Europe, it can be C3, but it can be also C4, mixtures of normal butane and isobutane. Gasoline, so C4 to C12 roughly, and it's a mixture of paraffins, branch aromatics, olefins, cycloalkanes, and aromatics. And to increase the octane number, you can increase this fraction and this fraction. The problem of increasing this fraction is that you can form some smoke, and it's easier to use this fraction. About the introduction of aromatics, petroleum companies started to increase the concentration of aromatics in gasoline in the 70s, let's say, or 80s, and in Europe, at least, the concentration of benzene in gasoline could be high. Nowadays, of course, it's regulated, and they don't use benzene. They can use toluene, xylene, and other aromatics. But it was a way to replace lead components, which were used before as to avoid, used as anti-knock additives. So when you want to use a three-way catalyst, you need to remove lead compounds, otherwise you will poison your catalyst quickly. And when you want to switch to unlead from lead to unlead fuel, it's a bit difficult to do that. And the way to do it was initially to increase the content of aromatics. and then of olefins. And we can use also some other additives. In Europe, they were calling this green gasoline by adding some ethers like ETB. Well, initially they were using also ETB, but ETB was banished because it can cause very strong pollution of underground water in case of accident. So this is for gasoline, and then kerosene or jet fuel. The international jet fuel is Jet A1. In the US, we use Jet A. So there are some differences in the composition and the specifications. And these fuels are composed of hydrocarbon ranging from C6 to about C16. And it's a mixture of paraffins, so alkanes, normal and isoalkanes, cyclic alkanes, and aromatics. And the fraction of alkenes, olefins, is very small because they could participate to the formation of deposits. So they don't want to have some plugging due to these. So of course nowadays, and I will present that on Friday, there are some renewable or synthetic jet fuels which appeared in the recent years. So the composition is different from the composition of classical jet fuels. Nevertheless, from one batch to another, the detailed composition can vary a lot, and especially in terms of cycloalkanes and aromatics. So the variation can be really significant, and then in terms of ignition properties, it can be also very different. Diesel, we are moving to higher carbon number. We were between 6 and 16. Now we are between 6 and 28 about. It's a mixture of paraffins, so also normal and branched alkanes, olefins, cycloalkanes, and aromatics, and naphthenoaromatics. So here the aromatics are much heavier than those present in gasoline or in kerosene. They have side chains, therefore they don't have only an aromatic behavior. Because of the long chains and multiple side chains on these aromatics, the certain number is increasing. The cool flame formation starting from aromatics is increasing. So they don't behave at all like toluene or xylenes that we have in gasoline, but they behave half like an aromatic and half like a normal alkane or isoalkane. And this is the same story for naphthenoaromatics. It's not a simple naphthenoaromatics. It's not like tetraline. But it's a structure with. I will try to draw something. So it can be a structure like this. but you will have here side chains. So it will be very different. And so again, for the olefins here, you can get some species like this with one double bond, but some here you can have some branches, and for these large aromatics, it's the same story. You can have the aromatic, and then side chains, even several side chains. I briefly spoke about additives. So ethanol, you know that ethanol is used in gasoline, but we will see some example where people try to use ethanol in diesel engines. And I mentioned ethyl terbutyl ether. So it's a tertiary butyl and ethyl group. And well, I wrote 3 carbons, so it's 1 and 2 carbon only. Right? Let's see if I can use this. One, two. So these are synthesized from isobutylene and ethanol, and we will see when we will be looking at the oxidation of biofuels that when you decompose or oxidize this type of additive, then you get lots of isobutylene and also ethanol. So these are the most popular additives which are used in gasoline nowadays. Let me stop here, and I will first try to answer the different questions that I got here. So which is the origin? So I say that you can measure it experimentally, and I will show that later on. Which is the origin of Ki? So this is my answer is that I will describe that in more details later on. Yes, there is a typo for N-heptane. As I said, it's C8 is isoctane. Another question, what is the combustion temperature limit that simplifications such as the use of the perfect gas equation do not generate errors? Above this temperature, what is the percentage error generated in calculations in chemical kinetics? Well, most of the computations are consider that we are operating with perfect gas. There are possibilities to compute real gas equations. The difficulty is that these equations are not available for every system. So I can hardly answer this question. How rates are calculated from experimental data? So you will use a reactor where you monitor the evolution of either a radical or a stable species, and you monitor it as a function of time, and then you will be able to extract the rate constant. I will show you again. I will show you later how it's done. I have slides for that. So I propose that we stop now. We have a short break, and we continue with this business of the effect of fuel composition. All right, so we continue. I want to go back to this slide where it summarizes the behavior of the fuel as a function of temperature. So here, if the fuel has a high certain number or low octane number, it will react. This will be good if you are operating a combustion ignition engine. It will be a problem if you operate a spark ignition engine. It seems I didn't push the right button. Okay, I'm back. Yeah, if in this temperature range, if you are using a high certain number, you will have a strong cool flame. If you are using an aromatic of this kind without long chain, long side chain, you will get almost no reactivity. If you are using something like a normal heptane, it's similar to an exotic, and you will get a cool flame. If you are using a branch fuel like isooctane, you will have a very small cool flame or no cool flame at all, similar to this guy. So now, when you consider a fuel, it's not a single fuel component. It's a mixture, and the fact that you are using a mixture, you will have within this mixture some. So for a compressed ignition engine diesel, you will have mixtures like this, which are not very reactive, which will reduce the overall certain number. You will have aromatics for which the aromatic part, the ring gear, doesn't react much, but the side chains compensate for that, and they can be still a good candidate for compressed ignition engines. And again, this is the same story for those presenting both an aromatic structure and a saturated cyclic structure next to it. So this part can react, and this side chain here, or there could be a side chain also on the cyclic the other cyclic structure here. Both of them will react and then will not diminish the ability of the fuel to autoignite. What my message is that the most reactive part of the fuel will contribute also to the oxidation of the other less reactive fuel components or fuel structures. Which means that these side chain compensate for the non-reactive behavior of the aromatic ring gear, but also when you have long paraffins, those by oxidation in the low temperature regime in the cool flame will produce radical which will be consumed by the other much less reactive structures like this or this aromatic ring here. So the most reactive part or element in the fuel drives the overall oxidation rate of the complex fuel. This is even something which I will show later regarding natural gas. If you consider natural gas as a mixture of, let's say, methane, ethane, and propane, compared to methane, neat methane, then ignition. I had a question about ignition delays. Ignition delays will be much shorter when you have these higher alkanes present in natural gas compared to methane. Methane will ignite very little, not easily at all, whereas natural gas will ignite better. And if you study the oxidation in a reactor, you can clearly see the impact of increasing the fraction of these chemicals to the oxidation of methane. So in that case, even if methane is the major component, the rate of oxidation of the overall mixture is driven by small quantities of higher and more reactive species, which are C2 to about C8 hydrocarbons. In the case of LPG, it's different because you start already with C3. So C3 is already a reactive fuel. But even though the presence of olefins, branch olefins, and branch alkane has a strong influence on the reactivity of the fuel. Let me elaborate a bit further. This is an example of a natural gas sample taken from the web. Well, I think that there is a problem with this first part. It cannot be C6 plus here. So there can be some oxygen and some nitrogen in this sample, and then you have the hydrocarbons here. You have methane, ethane, propane, isobutane, normal butane, isopentane, normal pentane, etc. And you can see that there is also presence of carbon dioxide, and this is very common. And if we were considering a sample taken from a different region on the globe, probably the composition would be much different. And sometimes the quantity of carbon dioxide and nitrogen is much more important than what it is in this sample, which means that the quality of natural gas can vary very much from one source to another. And here, with very high concentration of methane, this mixture is probably not very reactive in the low temperature oxidation range. This is an example of liquefied gas from petroleum. Because propylene is the most important component, I can claim this is most likely an American LGP. If it were a European LGP, we would have isobutane and isobutylene as major component. So you can see that beside propylene, you have many other chemicals here that range from C1 to C5. And some of them are unsaturated. Your propine is also called methyl acetylene, so there is a triple bond in this this component. And you see that there is another one, acetylene, which has a triple bond here, but present here. And you have some normal alkanes like well, ethane, propane. You have also normal butane, normal pentane, and you have branched hydrocarbons like isobutane, isobutylene, isopentane, and some dienes, so two double bonds, like butadiene and propadiene, which is also called alene. So it gives you a flavor of the composition of these fuels. And if we go further, with gasoline, well, there are many more compounds in the mixture. So it goes here from C4 to C9, and even even C8. And so the we can have a look at the different chemical classes which are present. So there are some normal alkanes. There shouldn't be too much of these, because more of these you have in the fuel, less the quality of the fuel will be, less the octane number. So, for example, you see peak 16, which corresponds to normal heptane here, but you have also traces of normal octane 24, and even nonane 28. But these are chemicals in very small concentration. And you can see that there is a large group of aromatics. And I'm a bit surprised that there are so many heavy chemicals here. But you can see that there are middle range aromatics with a branch side chain, and or highly substituted benzene, like 1,2,4 trimethylbenzene. So if we look at the small aromatics, there is a trace of benzene here, and again, it's probably a bit high, and toluene is the next one, and toluene is one of the main components, as well as the xylene, meta and paraxylene, which are not separated on this column, as it's usually the case, and orthoxylene. So xylene is draw. So the aromatic ring with a 2-methyl group, which can be in alpha, beta, or omega. So ortho, meta, and para xylene. And these are very unreactive in the cool flame temperature range. So it's good for improving the octane number. And then there are some other some other substituted aromatics like propylbenzene here or isopropylbenzene, which again are good for increasing the octane number of the fuel. And then those that we already mentioned, methyl-ethyl, there are different position for these, and trimethyl, where was it? Trimethylbenzene here. And all the others which are either higher molecular weight species. So these aromatic species will be responsible for the presence of a wide range of aromatics in the exhaust, unfortunately. Jet fuels, well, it looks a bit similar somehow. So this is an analysis of a jet fuel that we did in the lab several years ago. And so we could identify easily all the normal alkanes which were present in the fuel. There were some aromatics, well, similar to what we saw before, and in between, much less easier to identify. So the usually, I will show you that later. Usually kerosene is considered to be something close to C10, H20 something. C10 or C11, and it's mostly due to the fact that there is a peak concentration, let's say, of C10, C11 and C9 in these fuels. And we have been using a surrogate with global formula of C11H22 for a long time. So here the fraction of what I said before is that the fractions of olefin is very low to avoid as much as possible the formation of deposits and plugging injectors. I mentioned that nowadays there are synthetic fuels which are considered. These are two example different sources of jet fuel. One synthesized from natural gas to liquid. And we can see that compared to the previous one, well, it's somehow a bit similar. You have rather similar distribution among the number of carbon atoms. And another one with species that extend a bit further. So this one's, for me, it's can be described as a light jet fuel, whereas this one has a broader range of chemical formulas, carbon atoms. So from less than C8 and up to about C18. So here it was well on the low side. It was about that, and maybe a bit less on the high molecular weight range. So once you want to simulate the oxidation of this kind of fuel, you have to consider this distribution in terms of number of carbon atoms in the fuel components, but also the different classes of chemicals, aromatic, cyclic alkanes, normal alkanes, isoalkanes, polycyclic, And I will show some examples on Friday on the kinetic modeling that can be performed with different model fuels, and the effect of changing the composition of the model fuel, still keeping the global parameters of the fuels, such as a certain number. And this is an example of a diesel fuel, commercial diesel fuel that we analyze by GC. And you can see from this analysis that, well, the fuel, the global formula will be around C17, C16, because well, the C15 is the major compound here, but there is 16 and up to 21 and even further, which is not presented on this slide. So we could see here easily the normal alkanes. They were very easy to identify by GCMS based on their fragmentation spectra. And the other peaks are mostly cyclic and aromatic species. And now, if we consider a B20, which is a mixture of esters derived from vegetable oil and a diesel fuel, you can see on this chromatogram that there is a fraction here which is clearly coming from the diesel fuel itself. And then here, in this range, you have all these chemicals which are coming from the vegetable oil. So I will show also some examples of the oxidation of this type of fuel under controlled condition in the laboratory reactor. And you will see that we can relatively easily build reaction models for this kind of fuels. Nowadays, at least in Europe, these fuels are sold. You use it in your diesel engine at a level of, I think it's 8%. Below 8%, it's common diesel fuel nowadays. So I would like to summarize what I said. First of all, we had a look at what is combustion. So this is the oxidation of the fuel, which ultimately leads to the formation of carbon dioxide, water, and heat. This is also an exothermic redox reaction between a reductant and an oxidant, which are respectively the fuel and the oxygen from air. Incomplete combustion yields unburned hydrocarbon and soot, whereas NOx can result from the oxidation of molecular nitrogen. If we were considering fuels like solid fuels like coal, which contain organic nitrogen, with amines or other structures, then there would be also a formation of NOx, but through a different mechanism. I showed that combustion is very important for transportation, and about 99.9% transport is powered by combustion engines, either piston engines or gas turbine. Regarding chemical kinetics and modeling, I described that there is and there should be feedback involving experimental data and the construction and validation of models. And for that, we use global parameters, which are ignition delays. Those much depending on initiation reactions and also oxidation processes of radicals. We use also burning velocities, which depend strongly on H atom fluxes, their formation and consumption. And we use also detailed information, such as species concentration, and those derive from all the processes, not only from initiation reactions or only reactions involving H atom, but all of them. Different types of reactor are usable to produce data. They include the shock tube, plug flow reactor, perfectly stirred reactor, flames, mostly laminar premix flames or opposed flow flames. Rapid compression machines can be used to produce also detailed information, such as species as function of operating conditions, and to some extent engines. I'm mostly thinking about HCCI engines, where we can do chemistry. And I will show some examples about the use or importance of such studies. Global fuel properties are very important, and they include certain numbers for compressed ignition engine application, octane numbers for spark ignition engines, and the primary reference fuels for spark ignition engine octane numbers are isoctane, which has an octane number of 100, very little tendency to produce a cool flame, and normal octane, which has a strong tendency to produce a cool flame and has an octane number of 0. And for the diesel engine, compressed ignition engines, the primary reference fuels are normal hexadecane, which ignites very easily and has a certain number of 100, whereas methyl naphthalene, the other primary reference fuel, has a certain number of 0 because it doesn't tend to auto-ignite due to its aromatic structure and presence of a methyl group. And finally, we looked at the composition of the fuels which we burn nowadays, natural gas, which is a mixture of methane and higher alkanes, up to about C8. And its reactivity is very much driven by the presence of these higher alkanes. We also describe LPG composition. It is dependent on this one also depends on the region of production, but this one depends on the origin of use. So it's mostly C3 to C4 alkane and alkenes, but there are other species such as acetylenic or polyunsaturated. So in the US, it's mostly C3 hydrocarbons, whereas in Europe, it can be mostly C4. Gasoline, C4 to C12 hydrocarbon with more, with broader range of chemicals, normal and isoalkanes, olefins, cycloalkanes, and aromatics. And we've seen that these aromatics are rather light aromatics, and also that there is a large variety of olefins. Some of them are branched, some others are normal. The fraction of normal alkanes is relatively small to keep the quality of the fuel high. For air transportation, jet fuels are used. The most popular is Jet A and Jet A, but also Jet A1. So this is a mixture of C6 to C16 hydrocarbons. And again here, the broad range of chemicals, alkanes, cycloalkanes, aromatics, and very small fractions of olefins in order to avoid some deposits, injector plugging. And finally, the larger fuel we considered in this long list is the fuel appropriate for diesel engines, compressed ignitions. So with carbon numbers ranging from 6 to 28, and this is a more complex mixture of paraffins, iso and normal, of olefins and cycloalkanes, but also aromatics and naphtheno-aromatics. And here for the classes of species like aromatics and naphtheno-aromatics, which are not prone to react in the cool flame regime, they do react because of the presence of long side chains, which confer to these chemicals a behavior between that of an aromatic species and that of a normal alkane. And we also introduced the fact that nowadays we use oxygenated additives to gasoline in order to keep high octane number. And the two examples I gave was ethanol and ethyl tertiary butyl ether, which are somehow connected because ethyl tertiary butyl ether is synthesized from by dehydratation of the mixture isobutylene ethanol. All right, so I'm done with this first course, and I will try to answer to the different questions I got here. Oh, the first question. The guy doesn't like a green pointer. Okay, I could probably use a different pointer. Maybe I don't know if it's because it's not bright enough, or I have to figure out because on my screen it's bright enough, but maybe it's not so bright for you. Second question is, the RCCI engine researches are popular nowadays. Yes. Could you give some example about how we can change the fuel composition in an RCCI engine without using a second fuel? Well, I do not know. I'm not sure I fully understand the question, but I do not know the answer. And well, the last comment was thank you. So there's no real answer to this. Any other question before we close the session? No? Well, if not, I think we can close the session, and we will meet again tomorrow.